Okay, welcome back. We're gonna keep going with fluids. We're talking about flow rate today. Let's do it. Hey, so there's a continuity equation here that we have to deal with. So let's say we have a pipe. Here's the pipe. It makes a shape and it gets wider. The shape doesn't matter at all. But what we know is what goes into the pipe has to come out of the pipe, right? Sounds crazy. Now, what goes into the pipe is going to be a certain volume of liquid. We'll say volume 1. And what comes out is going to be volume 2. Now, this is going to happen at a particular rate, so we're going to have it per second. Okay, so we're going to have V1 over T is going to equal V2 over T. So if you put 3 units of volume in, you're going to have to get 3 units of volume out per second. Okay, now what that means is this area here is going to cover this distance, while this area will only cover this distance. So the smaller area here will be going faster than here, which will be traveling slower. The reason is because there's more cross-sectional area, so there's going to be less depth to get to the same volume. All right, and that's how it is. Now, this formula is going to be rewritten just a wee bit, okay? And we'll show you how. So if they have volume over time, volume is the same as area times height, right? The depth, whatever you want to call it, we'll call it H. This can be over T. Well, they're going to combine the H and the T together, right? Because here's what H would represent, and that's going to be in time. So that's also going to be a velocity. So this formula is on your sheet, and it is going to be A times V. This is going to be A1 and V1 is going to equal A2 times V2. All right. So A stands for area. By area, we mean cross-section area. All right, so that's going to be how big area it is in the pipe there. And the important thing is it's always got to be perpendicular to the direction that it's flowing here. Okay? I mean, you might have to do some trick, but I've never seen a problem like that that wasn't really bizarre. So you're going to have cross-section area. That's going to be in meters squared or something. And then over here, you have velocity. Okay? Now this velocity is called flow speed. Okay? Flow speed. Whereas this whole thing here is called flow rate. All right? Which is the same thing as the volume over time. So your flow rate is how many meters cubed per second you're getting, whereas your flow speed is just the speed of the water. So meters per second. Okay, now you could use any units for here. It could be centimeters squared and centimeters per second, as long as they're the same. It's going to be just like your combined gas law stuff from before. Okay, so these are your two equations. You might have to combine the two of them. So you might have to have a volume over time is equal to your area times velocity. That is fair game, all of that stuff. Let's do some practicing together. A major artery with cross-sectional area of 1 centimeter squared branches into 18 smaller arteries, each with a average cross-sectional area of 0.4 centimeters squared. By what factor is the average velocity of the blood reduced when it passes into the branches? All right, so we have a major artery. Here's my major artery. It's 1 centimeter squared for the area here. And that's going to branch into a whole bunch of little ones. All right, there it is. And there's going to be 18 total. Each one is smaller. Each one has a 0.4 centimeters squared. All right. Well, we know that the blood that goes into this area has to come out. It's going to come out in any one of these branches, but it's got to come out somewhere. So we know our A1V1 is going to equal our A2V2. A1 is going to be 1. There's only 1 centimeter squared. We're just going to work in centimeters here because it's easier. I mean, why convert everything just to convert it? So times V1 is going to equal A2. The area of here is 0.4. Well, kind of. The area is 0.4 for this guy and for this guy, but there's 18 of these things. So the blood gets to spread out to all of those, what do they call them, capillaries? Arteries, I guess. They're just smaller arteries. I'm sorry, anatomy people. Times 18, because there's 18 different spots for it to go, and those areas get to add together here. Times V2. All right, we're just figuring out what the factor is here, so we're going to solve for V2. So V2 is going to equal about 0.14 times V1. So whatever speed this stuff is, this is only going to be about 14% of that speed. All right, that's it. Let's do one that's a little different. Blood is pumped from the heart at a rate of 5 liters per minute into the aorta of radius 1 centimeter. Determine the speed of blood through the aorta. All right, let's draw a real life to scale heart. Looks great. So this is 5 liters per minute. Okay, and what it's doing is it's pumping the blood out. Here's the hole because, of course there is. And the aorta comes out here. Whoops. And it's got a radius of 1 centimeter. Okay, so we have to figure out what to do with this. So we're going to take this guy, do some converting here. Do you remember milliliters? I hope so. So this is 5,000 milliliters per 60 seconds. Right? Do you remember that? Anyways, so 5,000 milliliters is the same thing as 5,000 cubic centimeters per second, or per 60 seconds. All right, so combine that all together, we're going to get 83.3 cubic centimeters per second. So this is the flow rate here. Okay, now the flow rates have to be equal, so now we're going to calculate the flow rate in the aorta. Okay, so we're going to use A times V for this because we don't need to worry about volume here. So we're going to have 83.3 is going to equal the area. Well, it told us the radius, so we have to figure out the area. It's going to be a circle. So pi times 1 squared, tricky math, times V, which means that the velocity is going to be 26.5 centimeters per second. That's how fast the blood will be moving. Sounds awesome. All right, let's do one more. How large must a heating duct be for air moving 3 meters per second along to replenish air in a room of 300 meters cubed every 15 minutes? Assume the density remains constant. Right, that's the case for all of these. We're assuming the fluid is not compressible, which we'll talk more about tomorrow. But all right, we'll see if you can do this. We'll give you a chance. Pause the video, see if you can figure it out. We'll catch up to you after you finish. Did you do a good job? Let's find out. So the air is flowing in at 3 meters per second into this room, which has 300 cubic meters. And I want this to get switched out every 15 minutes. All right, so I've got 300 meters cubed divided by 15 minutes times 60 to change it to seconds. That's going to equal the area times the velocity, right? but I know the velocity, so the velocity is going to be 3. And there it is. Okay, so we're going to do some quick math here, and wouldn't you know it, cross out, cross out, cross out the 3's, make that a 1. So that times that equals that, and you get your area is equal to 1 meter squared. So it can be any shape at all, it just has to be 1 meter. Ta-da! All right, hey, that's it for today. Have some practice for you on the site. Smash that like button and subscribe, and we'll see you tomorrow.